Maybe. Good morning, everybody. So I think Professor Gerhard Kramer does not need a formal introduction. He said, just say, I'm from Munich and I'm here to give a talk. But I will say a few words anyhow. So Gerhard is a very well-known researcher in the area of telecommunication technology and information theory and applications. And he is a professor at the Technical University of Munich. And he will give us a tutorial on review of communication theory for key agreement by public discussion.
Yeah, I need that too, yeah. Yep. Yeah, it's getting mixed up at the back here. There we go. So now I think we're getting, it is on, yes, it is on, yeah. So thank you, Analia, for that nice introduction. It's nice to be here. Thank you to Ido for doing all the local organization work. It's always easier when all you have to do is send the invitations and then everything gets done for you. It's nice to be here. I'm glad there were a lot of people from outside also who came. So, and then of course there's the workshop in Eilat at the end of this week, which was one of the motivations for placing this workshop here. What I want to talk about is something that is, I was debating that's why the title took so long to show up, is debating what to speak about. I will talk about something that's relatively new to me. I learned it, I spent a month at DTU in Denmark in August, and for various reasons started reading up on this problem of key agreement. One of the motivations was that we had a project running now for 3 years in Munich on physical unclonable functions. I'll show you what that is. It has to do with biometrics, biometric security. And this is a more general version of the problem that was developed, at least in the information theory community. Well, it was motivated by quantum key distribution. So this was Bennett Brassard came up with their quantum protocols back in the 80s. And then Uli Maurer, who was at ETH at the time, started working on this problem and developing a classical, what I guess I would say is a classical version of this quantum problem. Or to put it in a different way, when you have a quantum exchange of quantum bits, you do a measurement. Once you do a measurement, you're in the classical world. And then you can start talking about certain problems. So it was a problem motivated from there. So this is a tutorial. I will try to go a little bit slower. I'm happy to have questions. I put in a break after about 40 minutes. That clock's a little bit fast, a little bit ahead. I put in a break after about 40 minutes and another break after another 20 minutes. So we'll just take a short break, like 2 or 3 minutes to relax and maybe start again. To begin with, most people here I think know this. So notations for entropy, where we take minus p log p, or the expectation of the negative logarithm of a probability distribution over the random variable, conditional entropy, mutual information, and the basic properties are the usual ones for discrete random variables. Then the entropy increases if we add, or doesn't decrease if we add another random variable. Conditioning on average, conditioning reduces entropy, which means that mutual information is bigger than or equal to 0 with equality if and only if x and y are statistically independent. Just to start simple, I think most people know this too, just to bring in the notation. Shannon's basic problem, point-to-point rates, B message bits coming out of the source. We have a channel which is noisy. Takes in X, puts out Y. We estimate the message at the receiver. We talk about a rate, the number of message bits divided, normalized by the number of resources we're using, which is N. And the problem is to find the maximum rate for reliable communications for small error probability, and remarkably enough, designing the code is easy if you permit arbitrary complexity. You can just fill in an array with randomly chosen letters from many code books, and then we get to the Shannon's well-known capacity formula to maximize the mutual information. Okay, quick outline. So the first part of the problem, I just review secrecy with a key. This is Shannon's perfect secrecy result. Problem 2 will be secrecy without a key. Very remarkable result from the 70s from Aaron Weiner on Wiretap Channels. Finally, I'll get to the problem proper. I try to point out the historical development of the topic, at least from the information theoretic perspective. A lot of it is based on Uli Maurer's PhD thesis. I'll try to point out where others contributed almost at the same time, especially Alsveda and Cesar. Try to point out where the differences are. It's kind of interesting to look through the history to see how, at least it was to me, to see how it developed. And then I'll go through various examples, a quantum key distribution example, which I think matches relatively closely to what the BB84 sort of does in the classical side. A binary erasure channel example, which shows a new principle, Uli Maurer's satellite channel, and then finally a mixed BSC-BC, which again is interesting for a very special reason, namely that the best known lower and upper bounds are still very far apart. So there's clearly room to do something here, and I think, well, I'll get to that at that point. So the philosophy in information theoretic security is a little bit of a different one than in what is done in practice, most practical problems. In most practical problems, we rely on complexity assumptions and computational security. Here the philosophy is different. We still do rely on assumptions, we have to, but here we're relying on modeling assumptions and try to prove something can be made secure rather than relying on complexity assumptions. So very much it's a question of what do you prefer. Do you prefer one or prefer the other? And certainly I think it's important to know about both. So here we prefer provable security based on modeling assumptions rather than computational security based on complexity assumptions. So let me begin with secrecy with a key. So I think probably a lot of you have seen this before, maybe not. This is the figure 1 taken out of Shannon's second paper, 1949 paper on the communication theory of secrecy systems. It's a very similar setup as before, except that the channel is noise-free and it is open, right? So we take a message, we're encoding it into something we send over a channel, and everyone can observe the channel. And we'd like to keep the message private, however, and to do that, we very often take a key. This key is secret and is shared between the transmitter and receiver. For the enciphering code, usually we use block codes. You can also use convolutional structures, but usually we take a block code, so it's some transformation which takes a key, takes a message, and then can be inverted with that key. Often the inversion is the function itself, or it could be, so it could be an involution, but generally you have an inverse function. And so you need to recover the message from the key and the so-called cryptogram. The goals here are what you might expect. We'd like to have a large entropy for the message, so we'd like to send a lot of bits. We'd like to use as little key as possible. We'd like to have a small entropy for the key. And we'd like secrecy. And the way we measure secrecy here is as a mutual information measure. We'd like to have what is seen in public to give little information about the message, and ideally even we'd like the two to be statistically independent, in which case we talk about perfect secrecy. And that's what interested Shannon in his paper. Probably the most fundamental result, it can be written out in just a few lines. So if we talk about perfect secrecy, and here we have the diagram of the message going in and coming out, then for perfect secrecy we need the mutual information to be 0, so that the entropy of the message is the same as the entropy of the message given E. Then we can add a random variable, the key, to here to get something that's not smaller. Then we observe that M has to be a function of E and K, so we can drop the M. And then using the fact that on average conditioning doesn't increase entropy, we get that that's less than or equal to the entropy of K. And so Shannon had this in his paper, and the interpretation is here that for perfect secrecy, we unfortunately require that the entropy of the key is bigger than the entropy of the message. And that, of course, means you need a lot of key, because if you are transmitting large files, you would need, for every bit of the file, in terms of entropy, compression, performance, you'd need one key. It also shows, it also suggests that you should first compress the message before encrypting it. So it does give architectural suggestions for how to design these boxes here. In fact, as I think many of you are aware, we achieve equality with a one-time pad, where if we take every symbol of the message, in particular if it's bits, and add to it a new random bit, then you can guarantee perfect secrecy, and you can check that the equality holds here and here for those problems. Okay. Now there's a lot of extensions you can do to this problem. So here I'm giving you one of the pages of Jim Massey's course notes. So he taught two courses on information theory at ETH from 1981 to 1997. In the first course, he covered basics of entropy. He covered random coding, Gallagher's error exponent. In the second part of the course, it was interesting. It was a different style of course. He first did groups, rings, fields, and then the second part was on algebraic coding, Reed-Solomon decodes, and the last part was on secrecy systems. And this is his diagram, and if you look closely at what's in here, the shaded part is already here in Shannon's model, but there's two extra things that he added. One is a private random source, and the other is a public random source. And it turns out that randomization, both public and private, can be very useful for secrecy systems, and we'll see an example of that in a moment, in particular with respect to private random sources. And so for this problem, since we've added two new random streams, we'd also like to keep those as small as possible. Of course, so in this example, you see that the notation changed a little bit. The message is X rather than M, and what is public is Y rather than E. But anyway, we'll get to that in a second. Okay, so that was a quick review of secrecy with a key from an information theory perspective, just very basics. Now let's get to Weiner's wiretap channels. So here the problem, very fascinating result, I think from the mid-70s. There's the Bell Systems Technical Journal paper of Aaron Weiner, showing that it's possible to communicate reliably over channels with noise without a key. Okay, and so the idea here is we have, again, a message, M. Alice wants to transmit this to Bob. We have a channel in between. Somebody's trying to tap. In this example, I think it's repairing an optical fiber, but it looks like it's tapping too, so that makes it okay, I think. Eve sees some noisy version of X, and Bob sees some noisy version of X. And what's important here is that the noise is somehow different, right? That's the key observation. That difference lets you do something. What is new too here is that we will add now private random bits to the problem. These play a key role in ensuring secrecy. So you need to somehow confuse Eve, and to confuse her, you need to do something random. Now Weiner looked at the special case where if we look at every symbol here and we model this channel as memoryless, then every X symbol causes Y, and Z is a noisy version of Y, so this is a degraded channel. We have a Markov chain. In fact, Aaron Weiner studied mainly, if you look in Rita's paper, mainly a noise-free channel between Alice and Bob, and Eve has a binary symmetric channel. That was the main problem he considered, and from that he used linear codes, coset codes, to prove what he needed to show by using a theorem of Elias on error probabilities of random linear codes, or of linear codes. So I'll quickly go through that. So this is a block diagram, which reflects what you just saw. Oh, I should say, so a few years later, not very long later, 3 years later, Cesar and Kerner published an extension of this problem to include here a general broadcast channel rather than having a Markov chain. I think that was quite an important result. The main thing they realized, I think, structurally, was that you have to actually add even more randomness than what Weiner had added. And I'll show you what that extra randomness is. So actually you will need 2 sources of private randomness, or you could view it as being more private randomness than what Weiner had added. And of course their main contribution then was of course also the converse theorem. So it's both an architectural addition to the problem as well as a converse result. Okay, so this is the, looking at this here, so what we're going to do is message M has B bits, so we'd like to send that message reliably to Bob. The random source will have 2 pieces, one here I've written with B1 bits, another with BV bits. And I'll call R1 to be B1 over N. The BV won't need a rate here, but it's interesting to think about because random bits are a commodity. They're important to consider. It costs something to produce true random bits. And Cesar and Kerner showed that capacity for a general broadcast channel looks like this. It actually has quite an intuitive interpretation. It's if you replace the V with the X for the moment, so suppose V was just X, you would have the mutual information from Alice to Bob reduced by some amount due to what Eve can measure, the mutual information between Alice and Eve. I think if you think about it a little bit, you might say, oh yeah, that makes sense. I mean, actually, we should reduce rate by some amount that Eve actually sees. Of course, actually achieving this isn't so obvious. In fact, the main role of replacing X with V is that what we do is we place a box in front of X, which is just a random channel. So the only role that the V has is to change the channel from going from X to, so if we have V here, we just build in a new channel to get the X, and then we have the broadcast channel, and then we view this whole thing as a new channel, right? So this here is just PX, Y, Z, given X, and here we have Y and Z, and now this whole channel is just PYZ given V. So it turns out, and now we can do coding from V to XY, we just have a new broadcast channel. It turns out that you will always make the channel from the new Alice to Bob worse, but you may make the channel from new Alice to Eve even worse, right? And since you're looking at a difference, it turns out that can help, right? So that's the role of this box here. And in fact, you could build it just with random number generators. But if you think about it carefully, suppose we have a continuous random variable here, like a Gaussian channel, then this might have to, like a Gaussian MIMO channel. A Gaussian, you don't need the V, it turns out, but for multi-antenna channels, you do need a channel like this. The V will be Gaussian too, but don't forget that to create a Gaussian from another Gaussian, how many bits of randomness will we need here? Well, an infinite amount. And so you can't build that. So you do have to worry a little bit about the rate of randomness that you are generating. That's why I'm emphasizing that. And there was a nice paper that appeared a little later by, I should know, Japanese researchers who solved this problem also with limitations on the number of random bits that you send. That's actually an interesting thing, because pure randomness, we don't know how to generate it, right, other than through quantum means, if you believe that quantum theory gives you, that nature really does give you truly random bits, which is the common belief, I think, by most physicists. In any case, that's the only role V plays. So in other words, we could do all this theory now without the V. We can just do it for X. Okay, and by building now a code from Vx to here is the same as building one from V to here with just a new V, right? So in any case, that's the role this plays. I emphasize here this requires more random bits. But now let's focus on the x. So suppose that v plays the role of x, and in some cases even you don't need this, for example, for Gaussian channels that are scalar. So just to repeat some of the comments I've made, the intuition is that the mutual information you get with standard codes is reduced by Eve's information. It turns out that the way you encode is you treat the random bits B1 here, the first piece, as new message bits. So you're just creating a longer vector of message bits. And then you transmit this longer vector from Alice to Bob. And then your rate is reduced by the random bits that contain no information. I mean, that's the whole idea. So R1 is, I guess I should have, R1 here is the rate of W. So you choose W to have length n times the mutual information from X to Eve, from Alice to Eve. And then, of course, M is limited to have the rate, the difference. So that's the whole idea. In fact, almost all designs of codes for this problem is you just take a very good error-correcting code, LDPC code, polar code, a lot of studies on polar codes now, spatially coupled code. Take your favorite error-correcting code and just replace some of the information bits with random bits. You know, and if it's a code that approaches capacity closely, then in general you can believe that it should make a good wiretap code. Of course, this needs to be checked, and then that's the interesting part in the design. Okay? Now, a common complaint you have here, practically, and it's one of the first things you hear, somebody always puts up their hand and says, wait a minute, what if Eve's channel is better than Bob's, right? Then the capacity, of course, is 0, right? We can't do anything better. Could mean many things, but here it would mean that the maximum overall input distributions of this, there should be a bracket here, but I should have said min of this and 0 is 0. Okay, how can we be sure this doesn't happen? Well, there are several replies I think I would give to that. First of all, so that's the pessimistic side, and then you talk about, oh, this is not practical and so on. However, I think in many cases this assumption is reasonable. Secondly, the methods that we use here will improve security in any case. Even, I mean, think of what spread spectrum did. Spectrum just scrambles things. There's no extra real security there, but it's still useful to do to prevent people who don't have the money to build, really good detectors to prevent them from doing things. The same thing will happen here. There still will be an improvement in the confusion towards someone who shouldn't be receiving the message. So I think that's reply number 2. Reply number 3, and that's one of the main points I want to get to here. Feedback actually breaks this bottleneck. And I think that was one of the main of Uli Maurer had several insights in his PhD thesis. This was one of the main ones. He developed feedback protocols that improved wiretap channel capacity. Of course, he was interested in another problem, but it effectively relates to the wiretap channel. Okay, so that's what I want. That's one of the main things I want to emphasize, and we'll get to the types of strategies that work. They have a very nice structure, very basic structure. Okay, so just to do an example for the wiretap channel, so let's look at Aaron Weiner's model. Y is X, except I'm replacing the BSC with a BEC. We know that nowadays BEC is nicer in some ways because it's easier to treat, of course. Not so long, but since 20 years we've been using BECs all over the place. Before that we didn't. And neither did Aaron Weiner. I mean, he was also interested in BSC. So if you look at the capacity, we just compute the mutual information from Alice to Bob. Since it's a wire, it's just 1. And the mutual information from Alice to Eve is just 1 minus the erasure probability. And if you take the difference, you just get P, right? So the bigger the erasure probability, for example, if P is 1, of course the capacity is 1, right? Because Eve sees nothing. To do a slightly more interesting example, suppose the erasure probability is 1/2. Then what we would naturally do is make the two pieces M and W to have length, where do I have it? Here it is, M to have length little n over 2 and W to have length little m over 2. And we can do a quick example of this. So the way to think of this is we have a message M. This has length n over 2, this length. and W. This has length n over 2, or approximately n over 2. I'll update it in just a moment to make a point on those two lengths, because it turns out that there's an interesting difference between whether you make m a little longer or a little shorter. Okay, that's going to be interesting, because Weiner did it one way, and the way we do it today is another way. It turns out I think Weiner's way is better for practical reasons that I will mention just very briefly. It depends on your point of view. Okay, but anyways, to send the vector length n over 2, we generate n over 2 random bits, and then we'll use an invertible matrix because we want to send at rate 1, right? Now, if G is invertible, of course Bob can decode. Bob just inverts the matrix, right? Now, what happens to Eve? Now, let's do a simple example, just length 2 code, right? So 1 bit of message, 1 bit of random variable, and we get to an example that also appears in the network coding literature. They like this sort of thing, right? Then what is transmitted over the channel is the random bit, and the random bit plus the message. And if you look closely, you'll see Eve can decode the random bit with probability half, right? But to decode M, Eve has to get both pieces correctly. And so then the probability is 1 minus p squared, which is a quarter. So we've already improved the security just by adding a random bit, right? That's the fundamental principle behind wiretap coding, exactly this. Okay, now what we do is just make the example a little bigger. Suppose we take m of length n over 2, w of length n over 2, and actually let's modify them a little bit. Suppose, and then I'll use a generator matrix. This should be a matrix with p1 here, a parity check piece here, which is square. I is square, and p2 is rectangular but almost square. Okay, so and then if we take this encoding, we get mp1 plus wp2 and w. Now, it's interesting to think of two ways of doing this coding. Weiner did it the following way in his paper. He made m a bit longer, which sounds a little weird, right? Because you'd think that you're not hiding as well, but there's a reason he did that. So he made this piece a little bit longer, and this one, of course, then has to become a bit shorter. And then his proof went as follows. Given m, suppose we know m, then we have a new error control code for w, and its rate will be slightly below the capacity to Eve. And so if it's a good code, Eve can decode. And by using the fact that Eve can decode, you can prove that the mutual information to Bob, Eve can decode W. Eve gets information, I should have said, can decode W, and because she can decode W, she gets limited information about M, epsilon. Okay, that's how his proof went. Okay, and that ensures security. Now, why is that a useful result? Because it's based on error correction. And error correction, we have nice bounds on whether Eve can decode or not, right? So it's very practical. All we have to do is develop good upper bounds on the error probability, polar codes, LDPC codes, spatially coupled codes, and can prove through that Eve's information is small. Okay, the nice thing is you have a mechanism to prove security this way. The other approach, which is more popular today, is based on resolvability, the work by Hahn and Verdu, who started this direction. So that is, in fact, the opposite. You make M a bit shorter and W a bit longer. And the nice thing you get out of that, out of this approach, you only get weak secrecy. At least using Weiner's proof, he used Fano's inequality and used that to show that if Eve can decode W, which he just proved by using Elias's result that good linear codes have small error probability. He limited the information about M. If you do it this way, you can prove strong secrecy. Now, I'll say a word about that in a moment, because it turns out converting weak to strong isn't that hard. You just have to hash a little bit. And that's a result that goes back to Bennett, Broussard, and Robert from the QKD community from the late 80s. Okay, and Uli Maurer knew that literature and then said, oh, we can get strong secrecy for free, right, using a little bit of hashing, just a little bit. You don't need much. And then you can convert this result to strong. And that's very nice, because to me that makes Weiner's result more practically useful, because we do have nice bounds on error probability. From that we can infer low mutual information, and then we apply a little bit of hashing, which everyone does anyway, to make things more secure, to make things more random, to prove strong secrecy. Yeah, proving it the other way for practical codes, I don't know how to do that. I really don't know how to do the proof for that case. I don't know any general mechanism to prove the mutual information between the one part. Suppose I have a good code, a polar code with, and I want to know how much mutual information does a noisy Eve get about some subset of the bits and getting an upper bound on that. I don't know of any mechanism to prove that. Okay? Questions? You're all so silent. Most everything is clear. Yeah. At high SNR, yes. Yes, yes, yes. That's true. Yes, yeah, I understand. So Shlomo's point, I think, is a very good one. I think he realized the point he's just making now, and then became an advocate to say, well, wait a minute. Usually, we only need very few secrecy bits, and then we start applying complexity methods, right? So it's not so bad that secrecy rate is low, and that's the same idea in QKD. If you in quantum key distribution, their rates are really, really low, and I'll show you why in a moment. Because they have to use protocols. They get really noisy channels, and so the rate is even lower than for Gaussian. It's really low. It's like 10 to the minus 3 or something. And then they use that to generate a 128-bit key, 256-bit key, and then applies that for symmetric key cryptography to go fast. So it's the same idea as public key cryptography. Public key cryptography is usually you don't worry too much that it's slow, because you'd only generate a key once in a while, and then for the fast encryption you use standard symmetric key cryptography. It's the same thing here. Okay, so I agree with Shlomo's point in this respect. Yeah. Yeah. Well, polar codes allow certain theory to be done because of the bounds that you have. They're the only codes I know for which you can do something like that. If you go to LDPC codes, you have to rely on simulations alone. But again, the nice thing is between these two approaches is this one here, you can rely at least on upper bounds on error probability to prove security. I think that's nice. But I don't know how to do it the other way. So for resolvability, there's one other thought that came to my mind. Now I popped out again, so I was going to say something. But I think it's an interesting problem. In fact, to get from weak to strong security, if you look at the proofs that the CS people have, it also requires a little bit of randomness, common randomness. Okay, so it's again, there's also something, there's a small weakness. It would be better to have directly, as you say, a proof of strong secrecy. And I think it's an interesting problem to, even for convolutional code where you have the full trellis structure. I don't know how to compute, let's say, the mutual information of 2 of the information bits given the output. Because if you think about it for a moment, it's a complicated problem. I mean, maybe you have to use machine learning methods to do this. I don't know, but even then you'll get some estimate, right? At least the error bounds give you something if you have a true bound. Again, so Weiner's approach gives you guarantees. The other approach, we don't know what to do yet in practice, I would say. Exactly. Absolutely. So semantic security refers to worst case. Now, for most of these codes, you can prove you get the worst case for free, actually. So I don't view that distinction. It's important to think about, but most, like random linear codes, you get it for free again. So it's not it's like showing the worst case error probability is low, right? That's what you're looking at. And you can prove that for these codes. Interpreting that in terms of other things might still be interesting to look at. Good. So maybe I move on to the final problem. So now comes more details, and we're going to get into feedback now. And I think there's a couple of new fascinating facts, and you'll see that the information theory still has big gaps. And so I really see this as an opportunity this area as an opportunity to make some improvements. Most of the QKD literature is going to use one-way communication. I'll talk about that in a moment, whereas you can do much better with two-way. Okay, I'll give some examples of this. It depends on the model. So this is Uli Maurer from his PhD thesis, appeared in 93. I think he was already giving talks on this on 91 or 92. This is his model. Okay, we have a satellite putting out public random bits, right? They're public. However, when they go through the atmosphere, they arrive with noise at Alice, with noise at Bob, and with noise at Eve. And the model he considered is statistically independent noise and hard decision decoding. Hard decisions, so it's a BSC. They're binary symmetric channels, which made the problem a little harder to deal with than if they were BECs. So I will go to BECs in a moment. It's much easier to calculate with. And the idea here is that both Alice and Bob should, from their bits, generate keys that are the same. So we want reliability. The two keys should be the same. And they are, okay, we want to be efficient, large number of keys, small, and then we're allowed to publicly discuss. So there's what you permit is public discussion. So the idea here is that you have an internet, you can send gigabits of packets back and forth if you really want to. This doesn't cost anything in this model. There's extensions to include rate constraints, but here it doesn't cost anything. In principle, we'd like small HM, and we'd like small randomness, entropy. And of course, we do want to guarantee, though, after all is said and done, that Eve, given what she sees, namely the public discussion as well as her bits, that the mutual information between the generated key and what Eve sees is small. And his idea, and this was, I think, one of the things he was really, pushing at the time, is he found protocols that showed Eve can be much more powerful than Bob. So it's not like the Wiretap channel. Because of the public discussion, Eve can be much more powerful than either Alice and Bob, and still you can generate secret key bits. Turns out at a very low rate. I'll talk about that in just a second, show you some pictures. But still it's possible. In fact, he showed that Eve can be arbitrarily more powerful. She just has to have some error probability, and then with appropriate protocols, Alice and Bob, even if they have really terrible channels, really weak receivers, they can still generate keys secretly from Eve. Okay, that was the main thing that he showed. Now, what I'm going to show you too is it's kind of interesting how he did this. He did this all without proving one coding theorem. Okay, and that's what I like about it. It was a very creative PhD thesis. He took theory from wiretap channels and applied it to this problem. How did he do that? Well, he switched the model in some sense by making Alice transmit something. So this is often called the source model in the literature, but what he did is he turned the problem around and he let Alice, and I'll show you how this was done, choose what to send, and then we get a broadcast channel to Bob and Eve. So here, look here, we have a wiretap channel up here. But with feedback, with public feedback. Public discussion is allowed. So this is a wiretap channel with feedback, okay? And that's key. So the feedback plays the key role in breaking this barrier that Weiner's problem had, okay? Now, it's actually interesting. This is called the source model. This is called the channel model, and the capacity of both problems is still open in general, including for the satellite channel. The common guess is that the key rate for the both is the same if, after optimizing P of X here, we can just we'll get the same capacity for both cases after optimizing. Here you're allowed to optimize, so in principle the channel model has a higher capacity because I can change the source. But if I fixed P of X, the assumption is that it's actually the same. It's not proved yet, though. Okay? A related problem I promised was biometric security. In fact, biometric security is a special case of this. Why? Suppose I'm only allowed to discuss in one direction. So this is one-way communication. Then it turns out that's an example. Biometric security is an example of that. So if I'm only allowed to send in one direction, suppose I have fingerprints. you know, I do an enrollment, say I have a noisy version, I maybe measure multiple times, that's what that diagram represents. Alice generates a key, stores some helper data, then later you measure your fingerprint again when necessary to authenticate, and then you use the helper data, which is this public discussion message, and the broadcast channel is the output here and the output here. Okay, and then you, depending on what Eve sees, you get different theories. Here the model is that Eve doesn't have any extra noisy version, so the problem becomes a little simpler. What is added in this problem is you have rate constraints on the public message, which is a little different than this problem. Here, the problem is usually stated without rate constraints. If you add those, then you wind up with the biometric secrecy problem. Okay. So there's a special case of the above model, but now we'll also include the storage. Entropy as a limitation. And we also added another thing where we want limited privacy leakage as well. So you're adding privacy constraint and a rate constraint. But you can add that to this model too if you want, right? And the most general version of this problem includes that too. That would be the most general problem, okay? So we have three problems intersecting here. You know, wiretap, this problem by wiretap with feedback, I would say, a very special type of noise-free and public feedback, and security. Physical unclonable functions is just another special case of this. That's just when the fingerprints become device fingerprints, but it's all the same. Okay, so it all comes together in this model with secret key agreement by public discussion, quantum key distribution, biometric security, puff security, wiretap channel with feedback, all fall in this framework, which is why I really like the problem. Okay, so it's a very general problem framework. So what I'm going to, well, I'll take a break in just a second, or maybe ask for some questions. This is the model I'm now going to discuss. This is the simple version. So we have a source. I'll talk about the source model. We have a source producing 3 random variables, one for Alice, one for Bob, one for Eve. We are allowed to publicly discuss. First, Alice sends to Bob, then Bob sends something to Alice, then Alice sends something to Bob, and then Bob sends something to Alice. And you can do this as much as you want. And what we're after, they have unlimited rate. We're after the maximum key rate. Uli gave this notation, SX double bar Z, XY double bar Z for the maximum secrecy key rate. Current situation, this is unknown for general sources. It turns out, so for many problems, Z is not available. If it isn't available, then you can show the maximum rate is the mutual information. Okay, so that is known. So if Eve sees nothing, just sees the public discussion, that's also a common situation that is studied, then it's the mutual information. Sorry? Yes, it is. It's open. Yeah, this is open. The only thing that's private is X, Y, and Z. That's what's special about it. Okay? Short break, just 2 or 3 or 4 minutes, then we'll start again.